Alright, so we are looking at Lagrange multipliers, and we're trying to maximize our function f. In this case we have three independent variables, and we're constraining it by g equal to a constant. So here we have 6x plus y plus 3z equals 22, and the function we're trying to maximize is 2x squared plus y squared plus 3z squared. And we're trying to find the maximum output of f of x, y, z. So I think the first good thing to realize is that this is going to be some kind of sphere-shaped object. In 3D, we have it centered at the origin. And it's going to go around here. And this is going to be allowed to grow out to some plane in space. And we're trying to figure out the largest output we can have and the largest this sphere thing is allowed to grow to. So we go back to our formulas for Lagrange multipliers. We have the gradient of f equals lambda times the gradient of g. And from there, for three independent variables, we should get three equations from here. We have the derivative of f with respect to x equals lambda times the derivative of g with respect to x. Same thing with y and z. Because we know that the gradients are defined as the partials of each function in the vector. That's supposed to be z. So from here we have three equations here. We have four unknowns. So we also need to incorporate our g equation because that's also more than just an expression, which is what we have for f. We actually have an equation because it's set to a constant. So from here we can start solving. I'm going to write these out into what their actual values are. So the partial of f with respect to x, the y and z terms disappear because they're constant, and we're left with 4x. And then with this side, we have lambda, and then g with respect to x. Again, the y and z terms disappear, and we're left with just 6. And then similarly with the other ones, we're going to have 2y for partial of f with respect to y, and this just equals lambda because we have a single y there. And with z, we're going to have 6z equals lambda times 3. So now we have these three equations and this equation to work with. We need to solve them for x, y, and z. And to do that, I'm going to just label these real quick. I'm going to call this equation 1, equation 2, equation 3, just so we can keep track of them a little better. Now over here, I'm going to start with putting everything in terms of lambda. So I'm going to take equation 1, and we're going to have x equals lambda times 6 over 4, because we brought the 4 over to the other side. We're going to have 3 halves lambda. Similarly with y is much easier. We're just bringing the 2 over. We're going to have lambda over 2. And then for the third equation, we have z equals lambda, again, over 2, because when we bring the 6 over to the other side, the 3 and the 6 will cancel 3. So now that I have everything in terms of lambda, I'm going to plug each of these x, y, and z values back into our original function, g. and we should be able to solve for lambda, which will give us our points. So, working over here, we're going to say we're plugging lambdas into G. Okay? So we have an x value here that we're going to stick into the x, y with y, z with z, and that equals a constant, and we should be able to solve for lambda. So to do that, we're going to start with 6x, so 6 times 3 halves lambda, and then same thing with y. Y is just 1, so we're going to have plus lambda over 2. And we're going to have plus 3 times lambda over 2. So yeah, just enough space here. This is going to equal 22. And from there, it looks like we have a common denominator of 2, so that makes this pretty easy. I'm just going to multiply these in. So we're going to get 18 lambda plus 1 lambda plus 3 lambda, this is all over 2, equals 22. And now if I add these together, I get 22 lambda over 2 equals 22. This gives me 11 lambda equals 22, and now we know that our lambda value is 2. Remember, lambda is just what we multiply the gradient of g by to get it to equal the gradient of f. So now that we have lambda equal to 2, we can now continue to solve these. I guess I should have marked these a little better. This is equation 2, this is equation 3. We can continue to solve these equations to give us our actual x, y, z values. So, plugging in lambda is equal to 2, we're going to have 3 halves times 2, which gives us 3. And this one's going to be 2 over 2, gives us 1. And this one's going to also be 2 over 2, which gives us 1. So now we have an x value over here, we have a y value here, and we have a z value here. So now we know that the point at which our sphere, when expanding, touches the plane, that's our constraint here, is at the point 3, 1, 1. So we have point 3, 1, 1. And we're not quite done yet because we're trying to find the maximum output of f, and we know that that happens at this point 3, 1, 1. So we're going to plug these values into our f function, get an output, and that will be our maximum in this case. So, I'm going to do that over here. Let's have so f of 3, 1, 1 is going to equal, so we have 2x squared, so 2 times 9, plus y squared, which is 1, plus 3z squared, which is 3 times 1. And this should give us 18 plus 1 plus 3, and this gives us 22. So you've successfully found through Lagrange multipliers that the maximum of f constrained by g is 22. And there you go.